Okay, this is 2.1 in your textbook, page 76. We're learning about representing powers up to degree 3 or 3 degrees in a sense. So, a couple definitions we need to understand. First is an algebraic term. So, quick definition is to just, algebraic term, this guy. Okay, so any of these are algebraic terms. Okay. So typically, this whole thing is called an algebraic expression, and then each individual kind of piece, so to speak, is called an algebraic term. And algebraic terms are separated by either a positive sign or an addition sign or a subtraction sign. Okay? When they're multiplied, like this 2 is multiplied by x squared, even though we don't see a little multiplication symbol there, it is multiplied, okay? It's not considered a separate term. This 2 and this x squared are not separate terms. When they're multiplied, they're considered one term. Okay? When they're added or subtracted, that's when we make that distinction between terms. Okay? So algebraic expression, algebraic term. Alright? So if I were to give you a very long expression such as this, I could say how many algebraic terms, and you might be tempted to tell me 1, 2, 3, 4. The only issue then I would argue is that these two terms can be easily combined into one term, right? So you would want to make that simplification first and call this 180, okay? And then there would be 1, 2, 3 terms. Okay? So separated by a plus or minus, but you're also going to make any simplifications that you can before you do that. Okay? Before you try and count them. So in proper definition, part of an algebraic expression, which is this whole thing, often separated from the rest of the expression by an addition or subtraction symbol. Okay, has 3 terms. So this example has 3 terms. 2x squared, 3x, and 4. Degree of a term. It's the sum of the exponents of the powers of the variables. Actually, I should add something in here. It's the sum of the highest exponents of the powers of the variable. Actually, sorry, if it's a degree, I was thinking degree of an expression. If it's degree of a term, yeah, you wouldn't need this highest, because it's just, we're just talking about these individual terms. So, as an example, if we're looking at this expression again, the degree of this term is going to be what? 2, yeah, it's just the highest exponent. Okay, it's the exponent of the term. The degree of this term is going to be 1. Okay, and the degree of this term, we don't have an exponent, so it would be 0. Okay, so 0 degree. Alright, so if we look at an expression like this, the degree of this term? 4. The degree of this term?
3.
No, it's going to be 4. And that's because it's the sum of the exponents. So you got to add 3 plus, remember there's an invisible 1 there.
Oh.
Okay? And finally, the degree of this term would be?
4.
So it's the sum of the exponents. Okay? The degree of an expression, so this whole expression, it would just be the highest one. It wouldn't be 2 plus 1. Okay? So the degree of this expression would be what? This algebraic expression, what is the degree? Yeah.
5.
It wouldn't be 5, it'd actually be 6.
Oh, there's 6.
Because you would have to add the x, the 1 to the 5. Okay, do you guys get that? But you wouldn't include this 2. So it's the highest exponent in the expression. That's how you get the degree. Okay? And remember, you still have to add these, the 5 and the 1. Okay? So the degree of a term, it's the sum of the exponents of the powers of the variables. So the exponents of the powers. So remember, this whole thing is a power of the variable. So x4, x3y, and x squared, y squared all have a degree of 4. So you're adding these exponents up. Any questions there? All right, moving on. So the whole concept in today's lesson is talking about how you can express degrees of a term, what we just talked about, in terms of like concrete materials. Okay? Concrete. I spelled that wrong. Oh no, I had it right. It just looks weird. Okay, so if we have one dimension, 1 degree, remember this x, there's a little invisible 1 that's up there, we can just represent it by a line. If we have 2 dimensions, we can represent it by a square. Alright? Because we're going to have 2 dimensions, so a square you can see is in 2 dimensions. I also put this in here, or xy. Because remember, if it's a rectangle, this length is not going to be equal to this length. But the degree is still 2 in this case. Okay, you guys see that? Because again, you're adding the exponents, which is 1 and 1. Alright? So this, even though you don't see a square in the actual term itself, it's still 2 dimensions because you have to add those 2 exponents. Same thing over here. So now we have a square or a cube where all sides are the same, x, x, and x. When you multiply all those 3, you get x cubed. Or you could have a rectangular prism, in which case your length here would be y, your width is x, and your height is x. Or you can even have a rectangular prism that's not square on one side, so you have all different lengths. So you could have y, x, z. Okay? And in which case your term would be x, y, z. All still in 3 dimensions. Okay? Any questions there? Alright, so we got a question here, example 2. What is the difference between 4t, 4t squared, and 4t cubed? Remember, just so we're clear, 4t squared is actually 16t squared. You guys do understand that, right? Because the 4t is in brackets, you still need to square that 4. The textbook has put it in brackets so that they all look very similar, but you need to make sure that you understand that 4t cubed, that 3, that exponent of 3, now also applies to the 4. So this is going to be 64t cubed. Okay? Any questions? No. Okay, so 4t, we know it's in 1 dimension because there's a 1 there, so we just do 4 lines. 4t squared, we know it's in 2 dimensions, so we're going to draw a square where each side has 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Notice we have a total of 16 sticks now. Any questions there? Okay. And finally, in 3 dimensions, we're going to draw a cube. So we have each side of the cube has 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And it's 3-dimensional. Any questions there? No? Okay. Moving on, example 3. It says a square has an area of 116 centimeters squared. What is the length of its side? So I put a little star next to square, not mentioned in the textbook, but this question would be very different if it didn't say square. Because it says square, we know that both sides are the same, right? So length and width are going to be the same. So really, we could say just L and L, right? The length and the width are the same. L and L. So if we know that then, we know that the area is 116, we know L squared is going to be 116. If it was a rectangle, we'd have to have another variable here. We'd have to have L times W equals 116. It would be a different problem entirely. Couldn't solve for L directly. But since it is, in order to remove the square, not sure if you know this or not, but you need to take the square root. These cancel, square root and the square. square root of both sides. So we have L is equal to the square root of 116. You guys seen that before?
Yes.
Okay. So the answer is 10.77. The length is approximately 10.77. What's wrong with this answer, besides it being slightly rounded? You can put a dot here or a squiggly line to say approximately. Anybody know what's wrong with that answer? It's not exactly correct. Michael? Did you have your hand up?
Sorry,
Okay, Josh.
You forgot to put centimeters.
Nope, that's okay. That's part of it. I put it here actually. Usually the units would just go in the final sentence answer. There's something wrong with this answer. Mark?
I think the answer should be squared.
Nope. Because it's a length, right? So it's only one dimensional. So it's definitely not squared. Because this was squared, right? But we took the square root of this, so this goes. It shouldn't be squared. Matthew?
It's not a perfect square because the number isn't bold.
Right, so I mentioned that. I said the approximation, besides that approximation. You're right, there's some more decimals here. Nobody knows. What's the square root of 25?
5.
Is it 5? What else could it be?
5.
Is it only 5? Be very careful. We're talking about integers here. We're in high school now. So we don't just deal in one dimension. Marnier. Right, so it's actually plus or minus 5. Okay. This is the answer to the square root of 25. Hold on a second. Because the square root of 25 is asking what number multiplied by itself twice equals 25. You need to know that negative 5 multiplied by negative 5 is also 25. Okay? The only reason we don't consider it here is because there's no such thing as a negative length. Okay? So that answer is disregarded. But don't lose sight of this. Okay, thanks guys.
Sir, that's